There's basically, in your textbook, they talk about 5 different attractive forces, 2 of which are bonding, like between ions, and so that's really the strongest one. So we're going to discuss the strongest ones first. Okay, so ionic bonding is just saying, hey, we have a charged thing here, it's negative, charged thing here, it's positive, opposites attract, and the closer they get, the stronger the attraction. And so that's why you would form a condensed phase. So most ionic materials are solids. An analogy for at least the distance dependence, you know that as you bring 2 magnets together, you get a stronger and stronger pull. Eventually, the gap, if you make it small enough, you can't separate them. They'll snap together. Depends on how strong you are. All right, so next to that is covalent bonds. That's where we share electrons. Okay, so this is what holds 2 atoms together, particularly 2 nonmetal atoms together. These are very strong as well. Very much stronger, but not quite as strong as ionic materials. And so covalent compounds will hold together under most temperature conditions. Very rarely will you see the bonds break. Okay, now we're getting to the point where we're going to discuss if we have a molecule here and a separate molecule here, what draws them together. Okay, so the strongest one of these is called hydrogen bonding. All right, so I'm going to put it in pink. And this is super important in biology. Okay, so basically water, hydrogen bonds, ammonia, hydrogen bonds, the amide bond in a protein, hydrogen bonds, all sorts of things, hydrogen bond. Okay, so that's kind of what holds us together. So in order to have a hydrogen bond, so this is the first of our intermolecular between 2 different molecules, you need to have certain conditions satisfied. And so we're going to use the example of water. So water has a lone pair, and we're going to draw it so that the lone pairs are in the plane of the board here, and that the water molecule, hydrogens are coming in and out at you. Now, this is probably not quite the best picture. Let me draw this picture a little better. So imagine this is going away from you, this is coming out at you. Okay, so we're laying the oxygen on its side like this. So the lone pair is up here and one down here. Right? So this is up in the plane of the screen, this is down. All right, so in order to have a hydrogen bond, first of all, you have to have an electronegative atom with lone pairs. The only ones that qualify are nitrogen, oxygen, and fluorine. If you don't have this, you have no hydrogen bond. All right, well, so far we haven't even talked about the hydrogen bond. This is the acceptor. This is what the hydrogen bond is going to donate a hydrogen to. All right, so this is just water. I want to draw the hydrogen bond by orange dots, dot, dot, dot. And usually it's 3 dots. And there's a hydrogen atom on another molecule. Now, since we're doing water, we'll do another water molecule. Okay, so the other water molecule has an OH covalent bond in the molecule. These are covalent bonds in the molecule. The hydrogen bond is between this molecule and that molecule. This is an intermolecular attractive force. This is why water is liquid at room temperature. This is a very strong interaction. So this is called the hydrogen donor. Since the OH bond is the covalent bond in this molecule, this is the donor, this is the acceptor. And the reason it's so strong is you have to have a partially positive thing, which basically only hydrogen is going to apply because hydrogen has no core electrons. And you need a partially negative on the acceptor, and it has to be on oxygen, nitrogen, fluorine. So the only way this hydrogen will be positive enough is if this atom is an oxygen, nitrogen, or fluorine, and this one's an oxygen, nitrogen, fluorine, only then will it be negative enough. Otherwise, we don't call it a hydrogen bond. Okay, so other examples of hydrogen bonds would be for example, if you have ammonia here, a lone pair, and you have something with an OH bond, it doesn't have to be water, it could be an alcohol. So this is methanol. Okay, the thing to realize is that this is for the collinear arrangement. This covalent bond is kind of pointing in the same direction as the 3 dots, which is pointing at a lone pair. This is actually how they're arranged in nature as far as they can. So any combination of 2 electronegative elements, oxygen, nitrogen, fluorine, one has to have a covalent bond with hydrogen, and that's the donor. The other one has to have a lone pair, that's the acceptor. One more example is HF. And the hydrogen bond has to be through attacking or bonding to so for example, 2 HFs can be connected through a hydrogen bond. This is the donor, this is the acceptor. F and F will apply. F and N, F and O, O and N. There's 9 different combinations that you can get from nitrogen, oxygen, and fluorine. All right, so that's the strongest, and that's what holds together, for example, water, liquid water. Something similar can help hold proteins together, and so on. Okay, these are very strong. All right, but there's very particular requirements. As the last example I'll talk about, these are what hold the DNA base pairs together in DNA. The double helix has no covalent bonds holding one strand to the other. It's all hydrogen bond held together. Okay, so if you don't have the conditions for a hydrogen bond, but you have a polar molecule, then you can have dipole-dipole. Okay, so we said HF can hydrogen bond. Well, HCl cannot, because the chlorine is not oxygen, hydrogen, or fluorine. All right, so let's look at HCl. It is a polar molecule, so let's see which way is the dipole moment pointing. It's like that, right? So chlorine is more electronegative. All right, so let's say there's another hydrogen chloride molecule. It has a dipole moment. How is that dipole moment going to want to be attracted to this dipole moment? Because opposite charges attract. So there's a positive end of another molecule and a negative end of another molecule. And so it would prefer, and of course it could be anywhere around, but let's put one next to it. It would prefer to have the next one like this, so that this positive end would be attracted to that negative end. Remember, this is delta negative, delta positive, delta negative, delta positive. Okay, so when you have a condensed phase full of polar molecules, the dipoles like to arrange themselves so that the opposite charge ends of the dipoles are closer for higher attractive energy than the like charges are, and they try to get away from each other as much as possible. However, there's a lot of compromises that have to be made. There's no way you can perfectly do this, because no matter what you do, there's still going to be some negative repulsion here and some positive repulsion here. The other way to kind of line these up is to do them head to toe. Okay, if you bring them in this way, then this will have a dipole this direction. This will have a dipole that direction. You can see that this arrangement has opposite charges attracted at the same end. These have opposite charges. So this is actually probably the strongest energy arrangement you can have for 2 HCl molecules. In a condensed phase, they're going to be all sorts of directions. All right, now what happens if you don't have polar molecules? You have only nonpolar molecules. Well, there's still a force that holds them together, and it's the weakest of them all, and it's called London or dispersion forces. And dispersion is a phenomenon where we have temporary dipole moments. Okay, so let's look at a hydrocarbon, a real long hydrocarbon. And it's going to be nonpolar because the CH bonds themselves are not very polar. Okay, and so on. All right, so when you look at this structure here, this is what a saturated fat might look like. Okay, so if you ever look at, meat, meat fat's solid, that's because all those fat molecules are tightly held together by these dispersion forces. All right, and so the dispersion forces are weak, but they're everywhere. Everybody has dispersion forces. There's dispersion forces in the HCl example, there's dispersion forces here, dispersion forces there. So these pink ones here, nonpolar molecules only have this type. Polar molecules have this type and this type. And special cases of polar molecules, which can hydrogen bond, have all three attractive forces in operation. So when we say, talk about this or that type of thing holding things together, we're talking about the most dominant force. Okay, so once you get to nonpolar, the only one is London forces. And so what happens is the molecules might be slightly nonpolar. Even if they're completely nonpolar, the electrons are moving around. And for an instant, they could be off more on one side of the molecule than the other. So that means temporarily it has a negative end and temporarily has a positive end. Okay? Well, the other molecule also has random movement of electrons, so temporarily positive, temporarily negative. However, when this one is slightly positive on a side close to it, that influences this one to be slightly more negative more of the time than slightly positive. So when you add up all the attractions and add up all the repulsions, it might be like 50.1% attractions and 49.9% repulsions. Well, that's 0.2% net attraction. So that's how these things add up. And that's why they add up for very large molecules in particular, because there's lots and lots of places where the electrons can create these temporary dipoles.